Devicetree began as the Open Firmware initiative at Sun Microsystems in 1988. Even though the Open Firmware standard is no longer supported, the Devicetree concept from it survived and is used extensively in Linux kernel and device driver development. Like with Kconfig, Zephyr borrows the Devicetree system to help developers build portable drivers and application code. If you have Linux kernel or driver development experience, feel free to skip this episode, as it will mostly be a review. But if you're like me and come from a mostly microcontroller background, these next few episodes will be extremely important. In my experience, it's probably the biggest hurdle to learning Zephyr. With that said, let's jump in. Previously, we looked at how Kconfig can be used to enable different software components. In this episode, I'll go over Devicetree syntax, how Zephyr uses it to define board-level hardware, and give you an example of how to use it to configure a button. The general rule is that Kconfig is used to configure software and Devicetree is used to configure hardware. Both are incredibly important in Zephyr. This 2006 paper by IBM advocated for a standard method of describing hardware to the Linux kernel. Because of this, Devicetree became the de facto standard for connecting the Linux operating system to device drivers and then configuring hardware at boot time. Zephyr uses the same Devicetree standard and syntax for describing hardware. However, it happens at compile time only, not at boot time like with Linux. The good news is that this creates a level of abstraction to help developers create portable driver code and application code. If you head to devicetree.org, you can see the specification for the Devicetree. Go to the specification and go down to whatever the latest release is. Here it's release version 0.4. You can get a PDF for this. It'll take you to a GitHub page, but then just scroll down and click on the specification link. Go ahead and open that and you can read about the specification for Devicetree. If we go to section 2.2, which I believe is here, 2.2, you get a diagram that's here that gives you an example of a Devicetree. The Devicetree is a data structure used to describe what drivers should be used for what hardware and the associated settings. While it is in effect just a text document, it creates this kind of tree structure. Each node can contain one or more properties. For example, these are properties, and one or more subnodes or child nodes. And you can see this is the root node as given by the slash, and this has several subnodes in addition to some properties. Like this CPUs, it has subnodes, CPU1 and CPU0, and some properties that are also associated with this CPU's node. A node can only have one parent, and that's what creates this tree-like structure. If we go down to 2.2.3, it talks about path names, and this is how you can address nodes along that path. It starts with the root node. Think of like the Linux file system, so this would be root, and then the node name, and then another slash, and then the next node name that's a child of this first one. And you can see an example of CPU's CPU1 from figure 2.2. So if we go back to figure 2.2, this is kind of like this diagram we saw here. It would be slash CPU's slash, say, CPU0 if you want to address this node, and then you can address the properties in it. If you go back to the table of contents, click on 2.3.1, this lists out some standard properties. This whole section 2.3 does. These are reserved key names when describing properties, and it means something to the Devicetree compiler, also known as DTC. Compatible is a special keyword used to find what's known as bindings. Bindings are the files, such as source code, configuration settings, and so on, that define how Devicetree data should be interpreted by the software. For example, using the compatible property, you can tell the operating system where to locate device drivers. In this case, it would try to locate a device driver that has the name of FSL, this is often the manufacturer, and MPC 8641. It would look for this device driver. You can list multiple compatibles. In this case, the comma separates them. It would look for this one first, and then if it couldn't find it, it would try to find a compatible driver with the name NS16550. Model is also a keyword, but I don't see it very much in Zephyr. You do see P handles quite a bit. But note that P handles are automatically assigned by the Devicetree compiler, as we will see. You shouldn't be assigning this property yourself. When you create a node like this one, and you run the Devicetree compiler, you can go in and look at the compiled, essentially, source for your Devicetree, and you will see P handles being assigned for you. So basically, don't use the name P handle and let the Devicetree compiler handle that for you. Another one you will see a lot is status. This just gives you the operational status, and you have several possibilities here. Note that these are strings. OK means that the device is operational, but in our case, for Zephyr, we will often set something to status equals OK, and that means to enable the driver. Or you will see disabled, which means don't include the driver or disable the driver. These others, reserved fail and fail SSS, these are generally for Linux only. Zephyr doesn't really use these. You will also come across number address cells and number size cells. These are used to configure the children in that node and describe, essentially think about the number of parameters you need to pass to that child node. Note that these are basically just strings. The # doesn't mean anything specific. This is just a string that's a specific keyword. In this case, it means number of address cells. And it's used to define the number of cells. In this case, think of number of elements in an array. And we see that the number of address cells is set to 1. We will see what this syntax looks like in a moment. There's a really good chart for this. You should have 1 address cell and 1 size cell. And it refers to the children nodes under this parent node. And you will see this set for the reg or register property, where you've got 1 address cell and 1 size cell. We will see this in use later as we examine Devicetree source in a moment. The reg property is used to address the memory or bus address of an associated device. We will see this when we start playing with the GPIO nodes, as well as things like I2C sensors that hang off of a bus. I haven't come across virtual reg or ranges much in Zephyr. And if we scroll down, you can see other keywords that you don't see very often in Zephyr. But there are several interrupt-related properties if you want to attach devices and device drivers to your processor's interrupts. We will explore interrupts in a future episode. If we go back to 2.2 and we look at that figure we saw earlier, hopefully a few of these properties start to make sense. So the compatible property lists the device driver we want to use, and the Zephyr build system, or I suppose the Linux build system in this case, will find associated drivers for this. In Zephyr, this looks for a bindings file that we will examine in the next episode, although you will see it briefly in this one. You will also see various properties defined as strings, in this case with the quotes. You have integers, you have hexadecimal integers, you have arrays that are defined like this with a space in between. And there are a few others that we will see in a moment. But note that this collection of nodes, subnodes, and properties, these allow us to configure our hardware devices and do so in an abstract manner that is separate from our source code. In general, it's a good idea to think about kconfig, that we saw previously, as configuring software elements, whereas Devicetree is more used for configuring hardware elements and things connected to our processor, or in this case, our board. So why should we care about the Devicetree? Can't we just include the device drivers with CMake or kconfig? The reality is that neither of those systems offers the level of complexity required to fully abstract away hardware configuration. Devicetree allows developers to write application code and drivers that are separate from each other and separate from the underlying hardware. It provides the glue that connects these pieces and layers together. And if used right, you're able to write application code or device drivers that run on any hardware. It also helps you map pins to peripherals and hardware to keep your application code free of such configuration. Devicetree syntax is a few decades old, and it might be a little confusing if you haven't worked with it before. Zephyr actually contains a really good chart to help you navigate that syntax. If you head to docs.zephyrproject.org, the version you're working with, which is 3.7.0 for us, if you go to the build and configuration systems, in here you can find some information about the device tree. This is the page we were just on. If you head to syntax and structure, this is a good overview, and I recommend starting with this. If you scroll down, you can find a chart that shows you the properties, but I found it was missing a couple. Instead, head to the bindings syntax and scroll down. You will find a better chart. I think this one's missing like the compound property type. So properties, which are properties in a node, they can be one of several different types. You have strings with the quotes. You've got integers with these less than, greater than symbols here. Note that it can go up to 32 bits, so keep that in mind if you want to put big numbers in here. There's booleans where you don't specify anything, you just name the property and that automatically sets it to true. If the property doesn't exist in the node, it's considered to be false. There are arrays, which are 0 or more 32-bit values, and that's specified like a single integer, but you have it with the brackets here with spaces in between your different elements. Once again, this is enclosed by your less than, greater than symbols, and note that everything in your device tree source, or DTS, must end with a semicolon, kind of like C. You also have unsigned 8-bit integers, and these are enclosed by brackets. This is useful for things like MAC addresses, and they're specified in hex. You have string arrays, where you've got the comma between the elements here. And you have p-handles. P-handles, as we saw earlier, refer to other nodes. When you see this address, that means it's using a label for a particular node. In this case, it would refer to the GIC node, which is not a property. Remember, a node is a thing that holds properties or other subnodes. As we saw, the DTC will automatically assign a p-handle property that gives a unique number to a particular node, and then we can refer to those nodes by using the label here with this ampersand. You can also specify arrays of p-handles, which I believe this is just a space between these two, much like you would for your 32-bit integer arrays. And then you have these things called p-handle arrays. They look like a collection of p-handles, but you'll notice that this second value is not a p-handle. This is just an integer. So in this case, we are referring to the DMA0 node, the label for that node, because we're using the ampersand here, and we're going to specify 2. The bindings file that we specify will use this as a sort of parameter in order to set something up. So this says, for our DMAs, we refer to DMA0 twice, and we're going to essentially pass it in 2 and 3, which could mean arbitrarily anything. Think of them like positional arguments that we would pass into a function in something like C. We get to specify what those mean later. In addition to specifying a label to a node, which we do with this ampersand, we can also specify a path to a node, starting with the root, and then as we saw, we can do slash, and then some node, and then slash, and then some node, all the way to the node we want to specify. The path to the node is going to be different than the label. So this path to some node might also have the label UART0, in which case these two would refer to the same thing. We will see how to set that up in a moment. Then there is a compound. I don't often see many of these yet, but this is where we can specify essentially an array of whatever we want. So here we have a p-handle as specified by this ampersand and the less than, greater than, comma, so this is essentially array, and then something else. We've got our array of unsigned 8-bit integers. Hopefully this chart gives you an idea of how to read device tree properties, which is going to be very useful when we look at them, change them, and make our own. So back in this device tree guide, let's go into our syntax and structure, the one with the OK chart for properties. But this is a really good primer that I recommend reading. Here's an example of a device tree source file, or DTS file. You generally need to have the required version listed at the top. This says to use version 1 of the device tree syntax. This tells the compiler what it's looking at and if it's supported. You then have the root node, And then nodes are specified in between these curly braces. And much like defining something like a struct in C, you need to use a semicolon to end these node definitions. So under the root node, we have a node. We're specifying a new node or a subnode under root. The only thing a node has is a subnode. There are no properties underneath the a node, but it does specify this subnode node label. So the actual name for this subnode is a subnode. So if you were to reference this, this would be slash a node slash a subnode. And now we're talking about this node. Or you can use the label without specifying that full path. This is the label. This is an arbitrary label that you can optionally add to make it easier to reference subnodes. So if we wanted to reference this, we could do ampersand subnode node label, and it would talk about this node, and you don't need to specify the full path. There's another example down here. If we keep going down, we see this fully fleshed out example of how we might specify devices on an I2C bus. These are fleshed out with properties and subnodes underneath the root node. So for example, in our SoC, system on chip, we might specify an I2C controller at a particular address. Note that this whole part here is a string. This is just an arbitrary string. The @ symbol does not have any particular meaning, but it is generally good convention that we specify the address for that I2C controller, and it should match this register address given here. The compiler doesn't do anything special with this address, but it does do something special with the address in register. So this is just convention that we write the address here for human readability. We then have that special keyword compatible that says which device driver we want to use. We are going to specify the Nordic NRF TWIM driver. The Zephyr build system will know where to find this. We will look at how it finds that and writing our own bindings files later. But this is just a string to say, look for this bindings file and use the source code associated with that particular driver, in this case, our I2C driver. In many cases, this will be provided by the vendor so that it knows how to work with the I2C driver of that particular chip. For the register property, we usually have the address followed by the size in memory of that particular controller. And oftentimes when you're developing for a processor that's been supported in Zephyr, this will be specified for you. You don't need to create this. But if you want to attach your own hardware, say to this particular I2C bus, you would need to add these nodes because these are your devices. So we're going to be adding devices and modifying the tree to include them. And usually it's hanging off of a particular bus. In this case, this I2C bus. Sometimes you'll have multiple controllers, so you'd have like I2C0, I2C1, and so on. So we want to attach this APDS 9960, and we want to attach it underneath this I2C driver. That may limit which pins you have available, but we will look at that later. Once again, we are going to use the address, but this is not a memory address. This is the address on the I2C bus. And as I mentioned, this is just more or less an arbitrary string. By convention, we give it the name of the device, @ and the bus address. And this bus address, by convention, should match the hexadecimal value for the reg property. This reg property is important. It sets the appropriate configuration information so that when the driver talks to our APDS 9960, it knows where it is on the I2C bus. So if you're able to change the I2C bus address of that device, you would then need to come back and change this reg property in your device tree source, and by convention, you should update this number as well. Here are some other devices, and they are configured very similarly. This would be on address hex 43, this would be on hex 1D, and that would give you 3 different devices on this particular I2C controller for whichever SoC we're working with, which I'm assuming is some kind of Nordic device. As I mentioned, I recommend reading this guide as it's a really good overview, and then using the table in the bindings syntax guide if you want to reference and know how to read the different properties. Back in the syntax and structure guide, there are 2 particular nodes that you should be aware of. One is the chosen node and one is the aliases. These are special keywords for node names that you should avoid using because they have special meaning to the Devicetree compiler. That being said, you are encouraged to create properties under these 2 different nodes because it can help you reference other nodes and properties in your own code. I find aliases particularly helpful when we want to define our own names for nodes. You use the chosen node to set up certain properties like setting the Zephyr console, remember this is just a string, to a particular device, say UART0 or UART1 or a USB device. This is how you can set various configurations for your board, like saying where the console should be piped to. Aliases is used for setting up shortcuts to nodes, and it's for naming convenience for the developer. So while you can use labels, I do find it very helpful to put your label here. So for example, this is a label for this serial device, and then give it some sort of abstract name that we can then reference in code. This is what allows us to remap names to help us abstract away our device-specific names. So for example, a controller might only have one UART and it's just called UART because that's what the vendor defined it as. Or maybe you want to use UART1 for a different board. By setting aliases and configuring your device tree differently per board, you can now have portable code because now you can say in your code, talk to my UART and use the board-specific device tree source where you know that my UART connects to some arbitrary UART device. So for your Nordic boards, maybe this is UART0. For your ESP32s, maybe this is UART1, but it doesn't matter. In your code, you just say, let's talk to my UART, and that's how you can create fully portable code. And it helps you avoid having to hard code that information in your source. If you head to docs.kernel.org, you can find the device tree sources coding style with the naming conventions for the different property and node names. Generally, you will see node and property names having the following characters, where it's lowercase characters, digits, and dashes. Note the dashes here, that's going to be a little bit confusing later. Labels for nodes, can use the same, but have an underscore. The exception is sometimes the node names will have things like this @ symbol, by convention to have the memory address location. But what can get a little confusing is these dashes versus underscores. So for example here, this node name is this string right here. You will see dashes in these node names. On the other hand, node labels will have underscores. Keep that in mind. And when we come back to the aliases, notice that this is a property name, so it's going to have a dash. So if there's an underscore in your label, you can't use that here. In many cases, I find that the Zephyr device tree compiler will yell at you if you try to use a dash or an underscore in the wrong place. And where it gets even a little more confusing is that when we go to reference this property under aliases in our C code, dashes don't work for macro symbols, so this gets automatically translated to an underscore. You will see this in action, so just pay attention to where dashes are allowed, say property names and node names, and where you should use underscores, which is going to be things like node labels. And if I didn't mention it, you will see node label given as the label, colon, and then the node name. If you don't see the label, that means that node doesn't have a label, so you'd have to address it using the full path from the root node. Now, let's look at how Zephyr sets a lot of this up for our ESP32 before we dive into creating our own example. Hopefully this will help you understand how boards are created and how to read device tree source. If you have not done so already, make sure that Docker Desktop is running, start up the Docker image that we've been using, or go to your local installation of Zephyr. So I've got the server running in VS Code. I'm going to connect to my host, go to localhost, and I'm going to make this a little bit bigger so you can see what I'm doing. Type in my password, and it's going to need to install VS Code Server. Once that's done, let's go to File, Open Workspace from File, and as usual, go to our workspace in the root directory. It's going to want my password again, and I'm going to make this a little bit bigger so you can see what's going on. Let's clear out all of the stuff from the previous episode, and here is our workspace. So in the Zephyr RTOS source code, we want to go to Boards. We're going to go to Espressif, because that is the manufacturer of the board we are using. And we're going to go to the ESP32S3 DevKit C. Here you can see a variety of DTS, which is device tree source, defconfig, and kconfig. We looked at this folder earlier when we were examining kconfig. This should hopefully help give you an understanding, or start to understand, how a board definition is created. If you want to, say, create your own board, you would create a number of DTS files in order to support your board, as well as your kconfig in order to set up your board for the software components. If we look at the kconfig, we can see the custom symbols that are created for kconfig. And no, I don't want this one. And no, I don't want to see those updates. Yes, I do want the recommended C++ extension. We'll let that install. And we're going to come back to our thing here. Now let's look at the CMake extension wants me to specify a kit. I'm just going to say unspecified. Back in our files here, we can see the kconfig for our particular board. This is also setting up the individual SoC, so we should remember that it's the room N8 SoC for the ESP32S3. The sys build sets up the bootloader options, which we won't play with here. Then we have the DTS files for the application CPU and the protocol CPU. If we look at these, you can see the Devicetree syntax that we saw earlier. Let's get rid of that terminal. This starts to define the configuration for a particular board. Notice the pound includes. This is a similar syntax to the C preprocessor directives, and this has the effect of copying and pasting this entire DTSI file. DTSI stands for Devicetree Source Include. So while a DTS file is used to define one or more nodes, DTSI is usually used as a common include among various DTS files. This should save you on things like rewriting parts of the device tree. So now if we track this one down, so this should be pointing to our SoC because it's not a particular board, which if you notice is not under here because these are boards. So hopefully this is helping you navigate the Zephyr RTOS source code as well and knowing where to find stuff, because I find looking at the source code for this particular project is helpful. If you come down to DTS for Devicetree source, you can find Extensa and there's Espressive. So here's the ESP32S3 and you can find the app CPU DTSI right here. It includes the common DTSI, which is this file right here. This is where it starts to define the peripherals associated with this particular SoC. And you can see that there are quite a lot here. You can see that there are aliases and chosen nodes already defined for us, and we can modify these as we need to in our own overlay files, which we'll examine in a moment. There are the CPUs that are set up under this CPUs node. So we've got CPU 0 and CPU 1. And I'm not going to go through everything here, so let's just look at an example. So I'm going to search for ADC. For our analog to digital converters, there are 2 of these drivers, and you notice that there are different channels with each one. Here you can see the address for this ADC driver and how many bytes that driver takes up. So this is 1 word or 32 bits. And then in the next address 4, we see the next one begin. Let's look for GPIO. Here are the definitions for the GPIO drivers in our device tree. There are 2 GPIO drivers. For the ESP32S3, driver 0 controls pins 0 through 31, and driver 1, GPIO 1, controls pins 32 through 53. That's given by this property number of GPIOs, or NGPIOs. You see here our compatible property. This is going to tell Zephyr which driver to use, and in our case, the manufacturer or Espressive will write these drivers. Writing your own can be a rather large undertaking if you're trying to add support for an SoC inside of Zephyr, which is why I recommend if you're starting with Zephyr, find an SoC and board that are already supported. I will take a brief look at how these work, but we're going to dive into this more in a future episode when we write our own device drivers. So let's copy this. And within Zephyr, we're going to search for that string. You will see a lot of DTSI files using this compatible property, but there's this YAML file. And this is fairly unique to Zephyr to use YAML because it's a fairly modern syntax for configuration files. This is a bindings file. The name of the bindings file, you can see here, Espressive, ESP32-GPIO.YAML, generally matches the compatible property here, which should also match the compatible property in the file we were just looking at, which let me bring that back up, and we can see that it matches the compatible string here. The file name isn't that important, but by convention, it matches this compatible property. The Zephyr build system, when it sees this compatible string here, it takes this string and it goes through all the compatible values in these bindings files and tries to match it to this string. That's why the file name isn't that important, but by convention, it should match this string. The best way to think about this is an interface file that specifies the properties for a Devicetree node if you want to, say, enable this particular device, in our case, a GPIO controller. As we've seen with a number of nodes, the reg property is required because it says which memory address, which device address on the bus, or in some cases, which pin number to use. And when we specify a GPIO node, we should do so with two parameters. In this case, the pin number and any flags, such as enabling a pull-up or active high or active low. The number of properties here should match the constant given for the number and then the name of the cells. In this case, it's this property here. Let's go back to looking at our board definitions. So if we go to boards, we're going to go down to expressive. We're going to go down to our dev kit C that we've been working with. And a common one is this pin control DTSI. You will see this appear a lot for your boards. So if you're creating a board, you're probably going to want something like this because it's how you attach pins to various peripherals. And in the case of the ESP32, we have a pin mux available to us, so we can have a UART driver attached to some number of pins as determined by the datasheet. In more simple microcontrollers, these pins might be set for us in the hardware and we don't have control over this. But for the ESP32, we do, and we need to set them in our device tree. As you can see, this includes even more device tree files or even these .h files. As we saw in the syntax, this ampersand means that we're referring to a label. And if we come over to this common.dtsi, we can see that label here referring to the pin controller node, which if we scroll up should be under the root node. This is once again defining a compatible driver for us, so Zephyr knows where to go find that source code, and it's going to set the status to OK, which means to enable it. If we change this to disabled, we would disable pretty much all of our pins on the ESP32, which we probably don't want to do, at least for this example. The pin control is a special node in Linux and Zephyr for configuring pin settings, which is what we're doing under here. These group names, group 1, group 2, and so on, are arbitrary nodes to group pin functionality. So you could, for example, set up a variety of flags here. All the pins in this group take on these flags or these effects. Pinmux is another property name where we can define our pins for a particular driver. In this case, we are setting these pins, so remember that less than greater than symbols means that this is probably a 32-bit integer, and with the comma, we have two of these to create our array. So you can see these groups in action, where for one I2C driver, we have two pins with the same effect, so it should be pulled up, they should be open drain, and output high, as opposed to UART, where we need to have separate transmit and receive pins. These are two separate nodes, so that one pin is output high and then the other pin is pulled up, because this is going to be an input pin. I mentioned that these are integers, and these look a lot like labels from something else. They are defined as preprocessor macros from this particular pin control header file. So let's go find that. Because it's a header file, in many cases you should be able to find this in your Zephyr-based directory. Let's go to include. We're going to go to DT bindings, and let's go to pin control. And you can see manufacturers have their own pin control or mapping files in here. So if you're creating support for an SoC, you would probably need to write one of these as well. This is part of the reason I recommend relying on manufacturers to have Zephyr support rather than trying to make your own, because it's quite an undertaking. So this file, ESP32S3 pincontrol.h, maps to this file. Let's open that, and you can see there are a lot of defines in here. So let's look for I2C0, SDA, GPIO1, so I'm going to copy that in our pin control file. Let's see if we can find that. And that is using another macro to map things. Hopefully we can right click and say go to definition. And in our ESP pin control common, we can find that definition here. So this is pin, I'm guessing signal input, signal output. So this should be mapped to GPIO1. And this should be mapped to GPIO2. Luckily, the names are here to help with that. If we look for UART0TX, I'm grateful that Espressif put the GPIO name here because now we can see that it is indeed attached to GPIO43. That helps us figure out where the pins are connected to these different peripherals by default. Like I mentioned, this particular processor has a pin mux, which allows us to redefine where those pins are mapped to by modifying these nodes. You don't necessarily want to modify this file because it's part of the Zephyr RTOS. We're going to create our own overlay file to do that. Now let's take a look at this devkitc procpu.dts file. Let's get rid of this search. You can see that there are more aliases chosen nodes in here than the app CPU, which makes it a little easier to work with the Pro CPU at first, which is why we've been compiling our code targeted for the Pro CPU rather than the app CPU. There's a lot more work to do if you want to get stuff running on the app CPU with Zephyr. I'm going to close out of these files. Let's say we want to create our own button that uses the button driver. In this case, it's called the GPIO keys. So we've got our buttons node that's under the root node. So anytime you have multiple files all referencing the root node, the compiler goes through and tries to combine them as best as it possibly can, giving priority to things like your overlay file if you were to say modify this. This is a node that's been created for us to handle the boot button that's on our board. It's different than the reset button, as that one's tied to hardware. This one is actually controlled by software. So anytime we use buttons, we should put it under this buttons node as it's been created for us, and it defines the compatible GPIO-keys bindings file so that Zephyr knows which source code to use. Here we have the button 0 label that's referring to button 0, and these names are rather arbitrary. It just allows us to reference them later. Once again, notice this underscore in this node name here. And we set up a few properties. This label I found to be optional. You don't actually have to have that label, but it can be useful. And this p-handle array can be a little confusing at first. Remember, we looked at these briefly. Here we're going to define a node, and this is how we set up using GPIO0, because GPIO0 on the board is connected to button 0, or the boot button. We're going to give it a value, an integer value, and then we're going to set some flags. So let's try to find out what this means by digging into the GPIO keys bindings file, because that is what determines how we set up these properties here. Remember that by convention, the bindings file should have this name, .yaml. So I'm going to search in all of the Zephyr source code. Let's search for this. And we're going to look for our YAML file. Oh my goodness, there are a lot. Well, instead of searching for the keyword, why don't we actually search for the file name, and we know it should have .yaml. There it is, gpiokeys.yaml. Let's make sure this stays open so we can see what's going on, and I don't lose it. We're going to examine this in detail later, but this is just to give you an idea of how you would figure out how to configure a GPIO pin. So keys in this case refer to like keyboard keys or buttons. Here we see that GPIO's p-handle that we saw earlier, that I was referring to here, that can be a little confusing, so we're trying to dig into how we set this up. It also defines a label and Zephyr comma code. The comma, remember, doesn't mean a whole lot. Just treat this as one string. When we're setting these up, we can also define things like the debounce interval, which is defaulted to 30, the polling mode, which is off in this case, and no disconnect, meaning don't disconnect the pin if you suspend the processor. We're going to leave this one alone for now, but we are going to define our own button by using these properties. So this p-handle array here, if we want to figure that one out, we can go back to this Espressif ESP32 that we were looking at earlier. So let's bring that up. And this is that p-handle array. So in there we have two cells in addition to that p-handle. So we've got a p-handle referring to that particular node, and then two cells behind it. So we've got this cell, and then this is one cell because that's just Boolean logic to OR these two together. We have the first one is pin, then flags. So we are attaching this to pin 0, and we are saying it should be pulled up and it should be active low. Finding out where these flags are for the pull up and active low were a little bit tricky. I had to dig into the repo. So in the include file, because these should be defined by a header file, that the Devicetree compiler knows what those values mean, we need to go back into DT bindings. We'll go to GPIO, and GPIO.h is a common include in many of these. And here are the different flags. So we've got active low, active high. We can do single-ended, push-pull, open drain, and here's our pull up and pull down if these are available to our particular processor. With that in mind, let's try writing some source code that reads from a button. Let's close down all of these files so we can start from a fresh interface. We're going to go into Workspace and we're going to create a new app. So here we're going to create a new folder for our project. We're going to call it 04_button demo. In theory, this should be fairly simple, but we do need to modify that device tree. As we saw with some of our previous demos, this can be helpful to create an overlay file for our particular board, which allows us to create truly portable and abstracted source code for our application. So in our button demo, let's create a folder. We're going to call this boards, and we're going to create a new file called esp32s3 devkitc.overlay. An overlay file, while this suffix doesn't matter too much, allows us to modify the device tree, and it's usually used for a board-specific or chip-specific type of thing when we're creating our application code. So you have DTSI for common includes, DTS for your source tree to define, say, your board's device tree, and then we have overlay, which are generally application or board-specific when we want to create our application code. We're going to start off by creating an alias underneath the root node. So we're going to say root node. Let's modify the aliases node, and you will see that this gets combined with all the other alias properties that were defined for us. And we're going to create a property my-button. Remember, property names need to have dashes, not underscores, but labels should have underscores. So we're going to attach the alias my-button to the node called button1 that we're about to create. I'm going to go ahead and end the root node with a semicolon, otherwise the Devicetree compiler will yell at us. Remember that buttons node we saw earlier, we're going to do the same thing. Under that buttons node, we're going to add our own. We are going to change the definition here of how those buttons work, but we're going to start by specifying that compatible GPIO keys. Next, we're going to increase the debounce interval to 50 milliseconds. We don't have to do this. I'm just demonstrating how you might change some of these properties to affect the functionality of this hardware. I later discovered that this debounce interval property is only used by the high-level Zephyr library called input that we won't use here. So it won't do anything for us in this demo, but it's still a good example of how to modify device tree nodes. We're also going to change it to polling mode instead of using interrupts. I will get into interrupts in a later episode and how to do things like pin change interrupts or timer interrupts. Then we're going to create our node. I'm going to give it the label button1 that we were referencing in our aliases node, and I'm going to give it an arbitrary node name. In this case, I'm going to call it D5, like you might find on something like an Arduino, because we're going to attach it to digital pin 5. Now I'm going to specify which GPIO pins should be used, and I'm going to do that using this p-handle array. I'm going to use the GPIO 0 driver, and I'm going to attach this to pin 5, GPIO 5. I'm also going to specify the GPIO active low and GPI pull-up flags. If we go take a look in the Zephyr source code, we go to DTS, Extensa, Espressif, we go into our chip, the S3. Let's go back into this common, and if you search for GPIO 0, you can find this is the label we are referring to. And because we're using pin 5, it falls within this range for this driver as opposed to, say, one of the higher numbered pins, which we'd have to use GPIO 1. So if you're using something above 32, you would want to change this to 1. So if this is like, I don't know, what is it, 53? So if we do like pin 52, this would need to be driver 1. But we are going to keep this pin 5, and I'm just giving it this arbitrary name for now. Convention-wise, this should probably be a button name, but whatever. I'm doing this just to demonstrate how you can arbitrarily name these nodes under this buttons category. The only thing I need to do here is add some semicolons. Notice I'm skipping like the label here because that is optional. Let's save this file. And we're going to go to our application. Let's create a new folder, src. In here, we're going to create main.c, and here we're going to develop our application. Let's do our standard include. So we've got our input-output, so we can do things like print things to the terminal. We will almost always need the Zephyr kernel header file, and anytime we work with GPIO pins, we usually need this GPIO header. I'm going to specify a sleep time 100 milliseconds, so we don't just completely spam our terminal when we're printing this stuff out. And then this is where things get a little interesting, because we need to get the information from the device tree in a way that we can use it in code. Zephyr does all of this with these special structs that have been created for us. And hopefully, if I've got my IntelliSense installed correctly for C, I should be able to right-click, go to definition, and you will find that Zephyr has this gpio.h file. I'm going to double-click to make sure this stays up. This is where this struct is defined for us. This is coming right out of that bindings file, so we will have the port that will be determined for us based on the port we specified here, which is 0. We also have pin and the flags, and we're going to get those numbers. So we're going to get pin 5, and we're going to get these flags in this other struct format. So if you go look at here, it is a uint 16, so it's an unsigned 16-bit integer. In order to get these out of the device tree, Zephyr has a bunch of these special macros defined for us, and I highly recommend looking at the samples. So if you come down here, let's collapse this, Zephyr has a number of samples defined, and Basic has some good ones like Blinky, Button, and so forth. These have simple projects that I highly recommend looking at to figure out what's going on and what special macros you should be using. There's a lot of macro magic, or as the Zephyr people like to call it, macrobatics, that happen to make all of this happen where we connect our code to the device tree. But this GPIO device tree spec get is defined also in this gpio.h header file. There's a lot of stuff in here if you're working with GPIO. This by IDX macro allows you to get multiple device tree nodes, and you would pass in an index. This allows you to loop through them and get multiple if you have, say, multiple buttons set up. And here it's going to fill out that struct, this GPIO DT spec struct, and fill out the port, in which case it calls even more macros to get that information from the device tree once that has been compiled for us. So that's how we turn a node into a struct in C. And there's this GPIO's argument here. So if we go back and look at this, we have this property. So we're going to get a property from the node. In this case, if we go look at our overlay file, it's going to go in here and get this property for us. So that's how we get the port, the pin, and any flags in our C code. Notice that we could use a different macro to say, give us this node by going through this path, or we can use a label, or we could use an alias. And this is why I like aliases, is because I could set up this alias for this board, and this is how I define buttons for the ESP32 on this particular pin. But let's say pin 5 is taken up if I want to move my code over to a Nordic board. I would just set up this differently, have a different overlay file, and when I build my application, it's just going to pull from the alias so I can have completely abstracted and portable code. Note that to get it from an alias, I need to use this DT alias macro. There is this overarching devicetree.h header file where the macro is defined here, and it does this macro magic to get the node from the alias name. And if we go to this definition, it looks like IntelliSense doesn't quite know where that is, so maybe I can find it. Define DT cat. Here we go. So there's a few here. This is a special thing that the C preprocessor uses to concatenate whatever A1 is to A2, and it allows us to create symbols by having concatenated names. So it's just concatenating basically strings, but they're preprocessor symbols. So my button isn't a string. It's a preprocessor symbol that the Zephyr build system knows what to do with, and notice the underscore because we can't have dashes. So the build system says, look for anything that matches this underscore. So it takes this and converts this to an underscore. So when we say my underscore button, this symbol matches up with the alias here. So it refers to this node over here so that we can get this information from this particular node property. I hope all of that made sense. With this struct, we can now define our button and get it to work. Let's create our main. We're going to have a return variable so that we can look for error codes, and then we're going to have a state integer to remember the button state, so we can just print it to the screen. Next, we're going to check to see if our GPIO is ready. The standard initialization pattern for Zephyr is to set up the drivers so that during the boot process, Zephyr automatically initializes whatever driver it needs or whatever device it needs, and then we just check this property. In this case, when you see the suffix _DT, it means device tree, so we're passing in a spec that we got from the device tree. It will often call an underlying function, in this case, device is ready, and all it's going to do is get that port information. So we could, from our spec, just pass in the port and use this function. So just be aware that sometimes you will see the device tree version of a function, and sometimes you will see the non-device tree version of a function. If you see the non-device tree version being used in sample code and it's calling functions in a driver, you will often need to pass in some property or parameter that is in the struct that you set up from the device tree. In this case, you can see it's passing in that port. Let's go back to our application code. In this case, all it's doing is returning a bool. So if we go to this definition and take a look, it's going to do all these system calls for us, and you can get pretty deep looking in your device driver. So just know that the interface here says we should check to make sure it's ready after it was initialized. Initialization during the boot process should happen before main is called. Main is your application code, but there is other stuff happening before that's ever called. I have not found a way to configure GPIO as input or output in the device tree, although that would be nice. I could probably do something like set a custom property here, read in that property, and then use that here if I wanted to, but just to demonstrate, you will need to call this GPIO pin configure function in order to set the GPIO as input or output, and you should pass it this flag. This flag should be defined in gpio.h, and this function should be defined in also gpio.h. Once again, this is the device tree version. If you weren't using that, you'd have to pass in the individual port pins and flags. Notice that it is taking extra flags here, and it is combining them with the structs device tree flags that we have set in the overlay file. For whatever reason, you can't do something like GPIO input. It just doesn't seem to work. So if you get that to work, please let me know. But for now, I found that I had to call this function manually in my code to set it as an input or output. Just to demonstrate how you might get some of these properties, I'm going to print out the flags. So remember, we've got this DT spec here. If we go look at it, we've got these flags that we can look at, and this should just be, I don't know, an unsigned 16-bit integer. So we're just going to go ahead and print that out so you can see, hey, you can define properties, you can still get the properties from things in the device tree, but note that in many cases, it absolutely has to match up with that interface, the bindings file we saw. If you don't match with that bindings file using those exact property names, the build system will absolutely yell at you. So that is part of how Zephyr enforces strict interfaces and maintaining good code when you expose stuff to user application code. Next, we're going to pull the button state. Now that we have our button configured, the GPIO has been configured, we're going to actually get the state from the button. And we're going to do that with this GPIO pin get. And once again, device tree form, I highly recommend going to the definition. And we can see once again that it's calling this non-DT version of the function. So let's go to that definition. And what's interesting here is that it is returning 0 or 1 for pin low or high, but it might change depending if you've configured your pin to be active high or active low, as we will see. And it can also return error codes that are standard within Zephyr. So if you look up the error codes for Zephyr, I don't want the latest, I want 3.7.0. Not that these are going to change. These are standard error codes used in usually Linux, and they are defined by this IEEE standard. So often you just need to compare to these if you want to find a particular error code, or if you see one of these numbers pop up in your application, you can just come and find that number here to get an idea of what's causing the error. So I highly recommend this page when dealing with error codes. Back in our code, let's go to main and continue our application. I usually like to print out the error code, and in almost all cases, the error codes will be less than 0. So you can just say, if your return value is less than 0, that's an error. Print it out and handle that error. In this case, we'll print the number and just say we failed to read from the button. And if there was no error, we will just print out that button state, which should be 0 or 1. Then we're going to sleep. We're going to use this kmsleep. If you ever want to see this definition, you can search for it. This is a common Zephyr thing. It's defined in the main kernel header. Some of this can get fairly complicated, but it's a really good, easy to use function if you just want to sleep the processor for a bit. Like any good Zephyr application, we should return 0 at the end, even if we never get there. Let's save our code. As with any Zephyr application, we need a cmakelists.txt. We will make the minimum required version 3.20 for cmake. We will tell it where to find the Zephyr package, because that's required for building it, and use the environment variable Zephyr base to do so. We're going to give our project a name, in this case button demo, and we're going to tell it where to find our main application code. Remember that when we find package Zephyr, Zephyr loads up and it automatically creates this target known as app. So when we do things like target sources or link to the app, we should use the app name here. Let's save this, and I can close that file. We must have a prj.conf, even if it's blank, and we can go ahead and build. So I'm going to open a terminal. Let's go to new terminal. It's going to have me select a workspace. Workspace is fine. Let's bring this up so you can see what I'm typing. And we're going to go into our apps 04 button demo folder. We're going to use West to build it. We're going to say pristine always in order to rebuild the build folder, if that does exist. And then we're going to specify our board as we've been doing. That will bring in all of the kconfig and all of the Devicetree source information from that particular board. Zephyr knows where to find all of those files because they've been configured in a particular way in the source code directory. Then for cmake, we're going to pass in our overlay file. To do that, we use the DTC overlay file variable that has a special meaning for the Devicetree compiler, and we're going to set that to the location of our overlay file that we created. We saw this for our basic Blink demo and others that we've worked with, but now it should make a little more sense of why we are creating an overlay file and how to create that file to modify the Devicetree to start connecting hardware. So let's build and wait a moment while that happens. Once that's done, let's take a look in our build directory. If you don't see it here, click the refresh. Go in here, go to Zephyr, and let's look for our fully amalgamated Zephyr.dts. This is what's created for the entire application. It pulls in all of that board DTS, all of the DTSI, all of the SoC specific stuff, and our overlay, and it creates one giant device tree. You can see there's one root node, everything is under there, all of the subnodes. And we also have our chosen and aliases at the top that set up the various configurations. And oh look, here's information that got pulled in from our overlay file. In fact, if we look for button_1, we should be able to find our label. So we have the buttons node. In here, we have the settings that we configured. We specified this in decimal, so hex 32 should be 50 in decimal, and we set up polling mode. These are the changes we've made. Button 0 was already defined for us as the boot button, like we saw in that Devicetree source file, and here is the button that we defined. Notice that we left out this code and label because we're not omitting any sort of code or anything. We just kept it as basic as possible. So this label and this node name are fairly arbitrary. You can kind of name these whatever you want, but this GPIO's property must be set so that the build system knows how to configure the pin, which pin to use for our particular button, and also which GPIO driver to use depending on the pin you want to use. So with everything configured in our Devicetree, we should have all of the necessary hardware set up, which includes not just things like pins and attached hardware, but also things like what RAM to use, how to talk to our flash memory, RTC timers. Yep, here's the flash memory partition table. All of this is internal and fairly abstracted for us, but if you were going to create a custom chip in Zephyr, you would need to set all of this up. So with that, let's try to flash our application. Open up a new terminal, because we want the server to keep running. I'm going to do PowerShell. I'm going to navigate into my Zephyr directory, activate your virtual environment so we can use the correct Python tools, and call the ESP tool to flash your device. If you see an error like this, it means your board is not plugged in, like I accidentally forgot to plug mine in. And we will try this again. Everything should flash. And now we can open up a serial terminal. Sure enough, we see our button state. When I press the button, that turns to 1. When I let it goes back to 0. So I can press this a bunch. Note that because we stated active low, this flips that state for us. So even though my button is wired to go to ground, 0, whenever we press it, this flips that output state. This allows us to abstract away either active high or active low buttons, depending on how you have the hardware set up. So just note if I state that, it means when I press the button, 1 appears, and when I let it go, we're back to 0. When you're done playing with that, you can exit with Control close bracket. And note that I kind of glossed over bindings. We're going to dive into them more in the next episode, but I just wanted to show you how to start working with and reading Devicetree source so that you can start connecting your own hardware to Zephyr supported boards. I highly recommend the next part in this Practical Zephyr series that you can find on the Interrupt blog. Here, Martin talks about a lot of the stuff we looked at, which includes reading the Devicetree source, how the syntax works, and how things are configured in Zephyr. This is a great supplemental guide to all of the things we just covered. Your challenge is to combine the LED demo from episode 1 with the button demo from this episode so that the LED turns on whenever you press the button. On the surface, this seems like a pretty straightforward and frankly frivolous challenge, but it requires you to combine the Devicetree overlay files from the 2 episodes. It's a good way to test your ability to read Devicetree syntax. Next time, we'll get into bindings files, which are mostly unique to Zephyr as they don't show up much in Linux development. They help define interfaces for Devicetree nodes and help connect such nodes to the necessary driver code. Good luck and happy hacking!